Today's section is on how we learn models. And this is really the sort of the first section on machine learning as far as this class is concerned. So, and it'll be particularly important for the rest of the semester going forward, so you should pay attention. So the beginning part of this lab is just some stuff to set up plots and so on and so forth. It's not really important. I'm not going to go over it. But here's the sort of table of contents of what we're going to go over today. And we're first going to talk about the process of learning and hypothesis spaces. From there, we're going to go off into what's the structure of the learning algorithm that we use. And it's a particular kind of algorithm called empirical risk minimization. We're going to go into what the consequences of noise are for this modeling. And from that point onwards, we're going to go and figure how exactly we actually do the modeling. Okay, so let's take a very specific example that we're going to work with over here, and the example is an election, and we're trying to figure out what are the odds of Romney winning an election in a bunch of counties. And we might think that this is based on the odds of his winning is basically based on the function of his population religiosity, race, poverty, education, and other social and economic indicators. And we'll just actually take one of them into account over here. Let's say the religiosity of the population in that particular county is what we'll take into account. Now, in all modeling, you have a certain notion of what you're going to put into this model. So as I said, you might have these various things like religiosity, race, poverty, and so on and so forth. And you might even actually have a causal model for how this works. Like, for example, you might say that people who are more religious are more likely to vote for Romney. And you might even be wrong in making this assumption. But in all of these models, when you do these things, you make some assumptions, and then you test out whether these assumptions work or don't. You know, your whole notion of there being a causal link between people being religious and voting for Romney may be wrong. There just might be a correlation. It may not be causal, but even if there's a correlation, that correlation might have predictive value. So your models don't necessarily need to be causal over here. They can just be correlative and still have predictive value for the answers you're trying to get. So generally, what we're going to do is we're going to have an input vector x over here. And it's just a bunch of features. And the bunch of features here might be your religiousness and other social indicators and so on and so forth. Then you have some function, which might be a linear regression, a logistic regression, something, whatever it is, which gives you an output, a response. And the response is sort of, you know, either the fraction of people in a county who are going to vote for Romney, or the probability of voting for Romney, or a 1-0 whether you voted for Romney or you didn't. That's the general structure of our learning problem, that you're going to have a y, which you want to predict, given a set of x. So you want to estimate f of x, basically. So here's a really simple model, which I have in this notebook, religion.csv, which you'll be able to access. By the way, this is a model I entirely cooked up, so there's no truth to it whatsoever. So let me put that disclaimer up front. And so let me assume, for example, that the Lord actually came by and told us that this is the plot that captures this model. So I'm telling you ahead of time. These are the various counties. There are more counties where, you know, in this sort of region of X, which is around 0.6 to 0.8. So where 60% of the people in the county claim they're religious. So there's more data there, but this is sort of the God-given, if you like, odds of voting for Romney given how religious you are, whereas 0 is you're not religious at all. And 1 is you're very religious, and that's the probability that you'll vote for Romney, or the fraction of people in that particular county who voted for Romney, to be precise. Now, in real life, we are only given a sample. We're never given everything here. We're not told all of these things. We're only given a sample. And so I'm going to assume that we are given a sample, which I'll denote by the script D over here, of 30 data points. And such data is called in-sample data, and we'll use this distinction throughout this class. There's in-sample data, which is the data that's in your sample, and the entire population can be called out-of-sample data, i.e. stuff that was not given to you. Okay, so we'll do a little bit of mechanism to basically get 30 of these samples. Not really important from the perspective of this, but it's just there for you to see it. And here are your samples. Having a little bit of trouble scrolling for some reason over here. Just a second. Whoa. Okay. And so these are the samples, and you can see them on the right side. That's the God-given distribution on the left over here, and those are the samples that you were given. So what we now want to do is to imagine that we've got a degree of amnesia, and this function's been taken away from our memory, and this is what's given to us, and we want to reconstruct the function that gave us this. So this is the basic problem. You're given a certain amount of data. You want to create a function which somehow or the other captures the data, and in capturing the data basically lets you make predictions in the future of, say, for example, over here where we have gaps. We want to predict it here, we want to predict it here, we want to predict it maybe there somewhere, and try and figure what the answer there was. Okay. The first thing we need to do to be able to do this is have this kind of notion of a hypothesis space. And the notion of a hypothesis space is basically a set of functions, if you like, which capture the zeitgeist of the data. So that's the thing we want to capture. And how we capture this is dependent upon what we choose to capture. We might, for example, choose to capture all the set of entire straight lines. So all possible straight lines with different slopes and different intercepts, right? So this way, this way, this way, this way, and try and capture it. We might say, well, that's not expressive enough, so let's actually include the quadratic functions. So our next set may be the set of all quadratic functions which captures this. The next set may be the set of all cubic functions. Our next set may then be the set of all straight lines, quadratic functions, and cubic functions. So we get a choice as to what we want to use as our hypothesis set. It's more sensible to do this in sensible ways, but you can combine any of these things into a hypothesis set that you want. So what we're going to do here is, just for the sake of concreteness, we'll capture, to start with, the set of all straight lines. And we'll do a fit among straight lines to this data. And to do this fit, we are actually using NumPy's polyfit function, which you can actually use to fit polynomials of any order to data. And later on in this section, we'll talk about how you can use scikit-learn to do this. So here I use polyfit to fit a straight line to this data. And it's not a bad fit to the data, but I think you will agree with me that there's something about the curviness of this data that the straight line doesn't entirely capture in a particularly good fashion. How did we calculate this fit? I'll come to that in a second, but in the meanwhile, let's sort of like formalize this notion of the best fit line amongst the various lines. So what do we mean by saying that this line looks like the best fit? Well, visually it kind of looks like amongst all lines, this might be the best possible line you could draw. But let's formalize this a little bit. And to formalize it, let's first kind of look at this notion that if I have a curve f over here, and I'm trying to capture this red curve f, and I'm only allowed curves which are expressive enough to have one wiggle in them, like g, this is the best I can do to capture this line, to capture this curve over here. And so no matter what I do, I'm always going to have some kind of bias. There's always going to be some bias between this line and this, because this is just not as expressive as that. So this is called bias, or I've also heard it called deterministic error, because this is just basically the amount of error you're going to get from approximating a function which is a one type with a function of the other type. Now remember that in our problem, we actually don't have this function. Remember, the Lord gave us amnesia, so he took this function away, if you like. So we have dual problems here. We actually just have data. We don't have the function that we're trying to get. And then we have the second problem, which is that we don't even know how expressive the functions we're trying to capture this data with ought to be. So we have to solve two problems here. Okay. So let's try something else. Let's try a 20th order polynomial. Why? Just for the heck of it. It seems to be something that might be expressive enough. So we try a 20th order polynomial. And voila, we can get a very nice fit. It goes through almost all the points and so on and so forth, and it looks very nice, and we're all very happy, and we go home, and we're done. We'll come back to that. We're not done. So we can calculate this bias, given that we actually know the function. And you can see that for the 20th order polynomial, which is this green thing here, the bias is much less than for the line. This is not surprising. I mean, visually, you could very clearly see that this 20th order polynomial did a much better job of going through this data. There's 30 points of data than the straight line did. Okay, so very quickly, what do I mean by the best fit 20th order polynomial, or what do I mean by the straight line that's the best fit? It's a very simple notion. Basically, what I'm going to do is I have this data. I'm going to drop perpendicular lines from the data to the perpendicular lines from the data to the line I'm trying to fit. And I'll do this for each and every line. I'll take these differences, and I want to sort of minimize that the entire difference. Now, I can't take the differences with the signs, of course, because if I did that, then this might maybe cancel this, and so on and so forth, and I'd get 0 in the end, and that's not very useful. So what I do is I square these. So you square these, right? You sum it up, and then you find the line which minimizes that sum of squares. Again, this is an intuitive notion, but we can formalize this a little bit by saying that what we are trying to minimize is what's called a error or cost or risk, which is basically a sum over all the points of the difference between the value at the point and the straight line that you're trying to fit. And what I'm going to do is I'm going to minimize this risk now with respect to the parameters of the line. And you know what the parameters of a line are. They're the slope and the intercept. So it's like a two-dimensional minimization problem. And that's going to give me the slope and the intercept, and I'll find the best fit line. And that's what polyfit does for you. So our game here is basically to do this minimization. And this notation argmin basically means I'm going to minimize it with respect to the function h1 over here and in the parameters of this function, this risk functional over all possible straight lines. Okay. We're not going to worry in this class much about how we do this minimization. In fact, that's what scikit-learn will do for you. That's what polyfit will do for you. We're not going to worry about the minimization process itself, but you should know that the game that we're trying to play is to minimize this cost or risk functional. And this is a game we'll keep continuing to play in all of machine learning. There'll be some risk functional, some cost, some error, which we want to minimize. So, is this enough to actually get the best fit amongst a particular set of things? In this case, the space of all straight lines or the space of all 20th order polynomials. It's not entirely enough, and the reason it's not entirely enough is this. Suppose I only gave you data about counties in which people are not very religious and asked you to make a prediction about those counties in which people are extremely religious. You will probably laugh me out of the room because you haven't actually given me any samples in that part of the space. So the second thing that you actually need for this to be a good thing to do is basically you have to put together this minimization process with a notion that your sample is in some way actually representative of the population. If your sample is not representative of the population, you will do a particularly poor job. So intuitively, you can look at this in this particular histogram that I've plotted. In the blue parts of the histogram are the entire data set, which we've been told to forget right now. But that's what the data looks like there, and this is what our sample looks like. And you can see that, roughly speaking, we have more samples in the space that where the histogram has most of its mass. And so, okay, we're probably in a good enough shape that our sampling is actually higher at the place where the population has more mass. And so that's kind of important. So there are two parts to this minimization process. And mathematically, we can state this as A and B, where A is that the error or the risk that we create, that we calculate on our data set, essentially, is the smallest on that hypothesis space. This is the straight line which gives us the smallest error. Or, if I'm talking about the hypothesis space of 20th order polynomials, this is the smallest risk on the entire space of 20th order polynomials. And remember that when I'm talking about 20th order polynomials, I'm fitting 21 parameters over there. So it's a 21-dimensional minimization problem if it's the 20th order space. It's a 2-dimensional minimization problem if it's the straight lines. And then the second thing that we sort of need for this to work is that the out-of-sample risk is roughly the same as the in-sample risk. And this is a restatement of the fact that we expect our sampling to be representative. It's basically trying to say is that what we really want for prediction, right, is we don't care about the points we know. For prediction, we really care about the points we don't know. So the out-of-sample risk is what we really want. But we don't have access to the out-of-sample risk because we've just been given a sample. So the only thing that we can calculate, right, is that we can calculate the in-sample risk, which is the risk on that data set over here. So we calculate the risk on the data set, and we hope that it's roughly the same as the out-of-sample risk. And one of the key necessary things for that to happen, basically, is that the out-of-sample risk, the in-sample risk ought to estimate the out-of-sample risk. And we need the population, the sample to be representative of the population for this to happen. If the sample is not representative of the population, there's no way on earth this is going to happen. Okay. So those are the two things. And so you can see out here, for example, what I've plotted out here is I've taken this 20th order best fit polynomial, and it does a great job on the population and not just on the sample. So it's actually kind of predictive. It does a good job predicting at these places where I don't have much samples. Okay, so now you're like, okay, let's go home. Everything's kind of good. We have this 20th order polynomial. We've solved the problem. We're done. The problem is that it's not that simple. There's this really bad thing in the world called noise. And noise is there for multiple reasons. Noise is there because you can measure things, measure things in a very precise fashion. For example, if you went out and you did this poll in various counties, you might not get people because they don't want to talk to you, or they don't have phones, and you haven't been able to contact them over phones, or they have cell phones, they don't have any phones at home. There may be other confounding factors. Race might be a confounding factor. In certain counties, people who are very religious may actually vote Democratic because they're of a different race. So there are various kind of modalities. And if you're not going to take that into account, these modalities are going to actually contribute noise to your problem. You can measure everything. Another example which you can think of can come from sort of credit modeling or mortgage modeling, in which case, suppose you and I are being looked at a bank for whether we should get loans. And it turns out that we have the same income, we make the same amount of money, and we both seem to be good. But the bank does not know, for example, that I've been divorced, and therefore, I'm probably more of a credit risk than a person who isn't. And so this is noise, that I may actually default and you may not. And so you might have exactly the same set of predictors, in a sense that you have my income, you have the size of my house, or anything that you might want to use, but you don't know this information about my marital status. And so there's noise between me and you. So noise comes for various reasons. One is not knowing things, and one is because things are just hard to measure. Okay, so let's go and in this piece of code out here, I'm just adding some noise to our little, sort of made-up problem. And this is what it looks like when I do that. So here I've added noise in. And these are the points that I observe, these squares. There's a little bit more noise here. This is the population which you are not supposed to know. You're supposed to have forgotten because you have amnesia, but I'm showing it to you all the same. And that's the line it came from. But imagine now that this red line is taken away, these green points are taken away, and these squares are what you actually see. Okay. So let's go and do the same fits we did earlier. And I'm showing you both the fits now side by side in this plot. So this is let's get rid of the click to expand output stuff. This is the straight line fit that we have to this data. Okay. It's still kind of like it was before. There's a slight rotation. You can see that it's rotated a bit from the old fit when there was no noise. And it does not capture our original curve particularly well, but it doesn't do a bad job in getting the general trend. But look what happens to our 20th order polynomial fit. And you can run this code and do it for yourself, and you'll see this. That our 20th order polynomial fit seems to do a reasonable job in a place where I have a little bit more sampling. But everywhere else, it goes completely cuckoo. So over here it's gone over here, and it's going to go up, and it's going to come down and do that, and out here it goes up, and then it tries to come down. So what's happening out here is that this 20th order polynomial is now trying to fit this noise. And this is a phenomenon of fitting the noise, which happens all the time in machine learning. It's something called overfitting, and if something is wrong with your algorithm in machine learning, the answer is almost always overfitting. And I'll show you overfitting, and you'll see it a little better in some other ways right now. But you can think about it from a very extreme perspective like this. You have 30 points here. If I give you the chance to interpolate 30 points, you'd say, well, if you give me a 30th order polynomial, I could go through each and every one of these points, right? And that would be like perfect. You've got on your in-sample data, you've got in your in-sample data very nicely, but the problem with it is that here you can see the 20th order polynomial is already very wiggly. Your 30th order polynomial is going to be very wiggly. It's going to go up and down. And it's going to do all of that kind of stuff. And so its predictive power is next to none. And this entire game is about predictive power. And that's why overfitting is a very bad thing for predictive power, because the noise makes things wiggle around so much that you can't predict at all with them. In fact, at this point, this is much better for being able to predict what's happening at a new point than that is. So here you can see it in slightly larger relief over here on this plot. Basically, that you can see how up and down this polynomial is going and how badly it's doing on the out-of-sample points on the populations. Okay. Let's make that same plot we did earlier, where we basically took the, this was a plot for the bias earlier, where we were basically showing how these two things were doing with respect to the actual curve, since we know in the back of our minds what the actual curve is. And you can now see that what happens is that G1 and G20, the noise structure is very different. There are places at which, if you remember at the previous time, G1 was kind of up here, and G20 was doing a very good job of fitting things. Now they're doing an equally bad job of fitting things, and there are multiple points at which G20 is actually kind of worse and has these spikes. And those are the spikes at which we have in-sample points which are very close by on this axis over here. Those are these kind of points, but the 20th order polynomial is way off. Okay. There's another way to see this. So what we said earlier was that there was an approximation error which came from doing this without any noise first. There's an approximation error which came from using the straight line to capture this curve which kind of looked sigmoidal, right? And so that approximation error was what we call bias. There's another kind of error in machine learning models, and that's called variance, and that's what we've seen just now. It's basically the error associated with overfitting. And what does it mean exactly, variance? So since I have access to the 200 points of the function here, what I did is and you can do it as well to see this, is I subsampled different data sets of 30 points from this. And on each one of those different data sets of 30 points, I fit my curves, my 20th order polynomial and my straight line to them to see what I get from them. And this gives you a very good illustration of what variance is. So I do that. And here's what you get. So here on the left side, what I'm doing is, remember, I have 200 points that God gave me. And in reality, I was only allowed to see 30. But now I'll behave like some superhuman being and take 30 points randomly out of these 200. And for each 30 points I take randomly out of these 200, I'll fit a straight line. And you can see that all of these straight lines, actually, there is some variation, right? But they almost all kind of go in the same direction, and they basically capture each other in a reasonably way, and they capture the zeitgeist of the data in a reasonably good fashion. Then the next thing I do is I take these 20th order polynomials, and I say I'm going to fit those on each one of these 30-point data sets. And by the way, I've taken 200 of them. I've taken 200 30-point data sets to do this. And now I fitted a 20th order polynomial on that. And as you see, where there's lots more data, okay, somehow the zeitgeist is not too bad. But the moment I get into a slightly less amount of data, I get hair. Because what's happening is that there's a different polynomial with its different wiggles because it's fitting different points and it's fitting different noise. And so I get a very hairy kind of structure when that happens, and I have nothing constraining where it is. And so this is a very, very good illustration of variance. You see what's happening is that just because I got a particular set of 30 points from these 200 points, my prediction at this point became boom. Just because I got something else, my prediction at that point became boom. And in effect, I can't make any prediction. And so this is why it's called variance. It's all over the place. And you can see this even more differently by actually looking at the coefficients of the fits. Remember, there are two coefficients for the straight line, the slope and the intercept. And there are 21 coefficients for the 20th order polynomial. Let's go and look at the coefficients. And we can do that, and we can plot these. And this is what you get. These are the coefficients for the straight lines. Look at the variation in those. It's really little. These are the 21 coefficients for the 20th order polynomial. Look at the variation. It goes from 10 to the 12 to 10 to the minus 12, depending upon which 30 points I chose to make the fit. And so this is like quite literally semantically why it's called variance. That is variance. So this is an illustration of what's happening when you use the 20th order polynomial. So you can see one of the very critical things out here is that you don't want to fit the noise. The moment you fit the noise, you lose all predictive power. Your coefficients are not constrained at all, right? And so you want to be somewhat more, if you like, conservative about the model which you use to fit the data, simply so that you don't overfit. Now, how do you diagnose that you've got overfitting? That's one of the big questions that you want to answer. Okay, so let's go into that a little bit. I'm just going to save this these 30 points into a data frame over here, if you want to use it to play around later. To do this, we make a sort of like an observation about this data. A priori, you don't know what your data looks like, and you might try and actually, do something like what I did over here. But remember, you have only one function. You have only one data set. You have only one set of 30 points. You don't have the ability to do this kind of plot. This one, or the little hair plot over there, because you don't have those remaining 199 sets of 30 points to do this. You have only one set of 30 points. So how do you diagnose that you've got overfitting going on? To do this, you make this observation that, okay, I've got the sample of 30 points, but what if I held back some points from that sample of 30 points? So would I pretend that out of those 30 points, about 5 or 6 of them did not actually belong to that sample? And then I can check. I can do my fits and everything on those 25 points, and I can check how I'm doing on those remaining 5 points. So this is called the process of holding out, or splitting your data set into a testing and a training set. So what we're going to do in general, so this is just a sort of idealization of it, that you're going to take your data, maybe you're going to split 4 parts of your data into a training set and 1/5 of it into a testing set, where you're actually going to test what you did. Okay. So let's do that, and this is the first example of a function that you're going to use quite often in this business that you'll see. It's this function called test train test split, and what it does for you, and it comes from sklearn.cross-validation, and it lets you split your data set basically into into different sizes of training and testing. So what I've done out here is basically I've split the integers between 0 and 29 as an index into a training size of set 24 into a training set of size 24 and a test set of size 6 over here. And then I'm going to use those indices into my data frame to basically get the training set of x's and the responses associated with this training set of x's, the testing set of x's, and the responses associated with the testing set of those x's over there. And now I can plot these for you, and you can see the difference. So basically what I've done is I have split this up. The blue squares out here are the training set, and I have 1, 2, 3, 4, 5, 6 points in the test set over here. So now all the training I'm going to do is going to be on these blue squares. I'm not going to take those green squares into account when I do it. I'm only going to use the green squares to test stuff. Okay. So while we do this, this is a good time to make a short digression about scikit-learn, because this is going to be really useful in all the stuff you do in your homeworks and in the labs and so on and so forth. Scikit-learn has a lot of utility functions like train test split, which we use right now, but really what's really very nice about it is its API. The API of scikit-learn is really simple. It has an estimator interface for building and fitting models, a predictor interface for making predictions, and a transformer interface for converting data. There are really just 3 interfaces in it, and you'll see them. So let's actually do the same polynomial fitting out here, and this time I'll go into it a little bit more detail because I want you to see the structure of scikit-learn. I didn't go into polyfit because that was just to make an illustration. So to get you familiarized with scikit-learn, let me show you what we're trying to do. So if I have a bunch of points with values 1, 2, and 3, what I want to do is I want to sort of make them look like this. If I'm trying to do a polynomial fit. So this is a constant. This is the x squared, x cubed. And you can see this. This is the structure I will always want in scikit-learn. It's always going to be down the axis like these, in the rows, the samples. So I have a sample 1, 2, 3. That was my x. This is all I would need if I was just doing the linear fit, and the constant, of course, but that's a different matter. But now if I want to do a polynomial of third order fit, I need to have constant x squared, x cubed, and those are my features. Those are what I'm going to call my features. Those are going to be my 4 different features over here. And then going down this are my samples. So it's always samples as rows and features as columns. And that's the structure that scikit-learn takes, no matter what algorithm you use. And so to do this, I use a code which looks like this. And all the code in scikit-learn always looks like this. So what I'm trying to do is I'm trying to get polynomial features. I'm going to trying to get polynomial features up to degree 3. And to get these features, I fit. And to transform them into this particular structure, I use fit transform. So I do a fit transform on 1, 2, 3, and you can see I get that over here. These are the constant terms. That's the linear terms. That's the quadratic terms. And that's the cubic terms. Cubic feature, quadratic feature, linear feature, constant feature. Sample number 1, sample number 2, sample number 3. That structure is going to be constant. So we're going to make features now from our x's, and we're going to make them for each one of these degrees, and that's what I'm doing over here for the train and the test. I'm taking the training set. I take the training set and I reshape it with arguments of -1 and 1. And this is just a little bit of technical stuff. Typically vectors in NumPy and pandas and all of these tend to be vectors like this. And if I want them to be vectors like this, which is the kind of shape I need for scikit-learn and NumPy, I need to do reshape of -1 and 1. It's just a little technical point, but something you'll probably, it's kind of part of that dirty stuff that you have to do before solving problems. So it's good you see it once and for all over here. And so if I reshape 1, 2, 3 with -1 and 1, I'll get it in this shape. And that's the shape scikit-learn needs, basically. It's a matrix of rows, 1 row per sample. And there's only one feature here. Now what the polynomial features that fit transform does is it converts it into something like this, where you're going to have a array of arrays, and each one of those arrays corresponds to each sample, and this is going to have the stuff corresponding to each and every, the zeroth order, the first order, the second order, and the third order. And so that's what this does. You see polynomial features of D that fit transform, train set dot reshape of -1, 1. And we're doing that for the training set and the test set. And we're basically doing that for each and every degree in this make features function. So we're creating, depending upon the number of degrees we have over here, and I think we're going up to the 20th order, right? Because we're 20th order polynomials. We're creating 20 different training sets and test sets, each of which is something wide like this. And when you go to the 20th order, there are 21 features in here, basically. This same structure is actually used to do is used to do the training as well, and we'll see that over here. And so this is the kind of structure we're setting up, basically. So we have training data corresponding to the various features like that, and then we have 1s and 0s as our response, or if it's not 1s and 0s, it's the actual values. In a regression, it's the actual values. In a classification problem, it's 1s and 0s. And we have a similar structure for the training part and the test part in here. Usually the test set is smaller than the training set because, after all, you do want to keep data back for doing training as much as possible. Okay. So here's an example. This is the third thing in the list, so it corresponds to going up to the third order polynomials. This is the training part, and you can see what it looks like. It's an array of arrays, and each of the lists inside this array is the list for each sample. And the y's are just basically a simple usual array that you're familiar with and love. And similarly for the test set, which is smaller. Okay, so to carry out this regression, this polynomial regression, what we're going to do So we're going to import linear regression from sklearn. Okay. We're going to make the features in train test lists. And we're going to go up to degrees. We're going to go up to the 28th degree. So in this part, we are setting up 20 data sets. And now we're actually going to fit. So for each degree, we're going to get a training set associated with that degree. That's there. We're going to get a test set associated with that degree. Okay. We're going to set up the model. And this is how every scikit-learn model works. So once you know how to do any one of these, you know how to do all of these. If it's logistic regression, you put in logistic regression over here. If you're trying to do some kind of classification and you're doing, and if you're doing a SVM, it's exactly the same structure. You put SVM over here. Then you fit it. And fit always takes two arguments. The first argument is the features matrix, right? That's that matrix we saw up over there, which had this one over here, which had each row corresponding to the to a different sample, and each column corresponding to a feature. Okay, let me go back there. Here we are. Okay, so you set up the estimator. That's the linear regression over here. You fit it to the training set with the training data, and then you predict. And the predict function, so you see this is one key interface that you need to know, which is a fit. Always two arguments, always a features matrix, and the response. And then you predict, and you always predict on whatever you want to predict for. So out here, I just want to predict on the training set. So I do, which is kind of hokey, right? Because I'm predicting on stuff I'm learning from. And this is the real thing. Here I'm predicting on the test set. So I just take a predict. Predict takes one argument exactly, and that one argument exactly is the feature matrix on the test set. Okay. And what I'm then going to do is I'm going to calculate the mean squared error between the training response and whatever the prediction on the training response was. And I'm going to calculate the mean squared error between the test response and whatever I predicted the test response to be. So this will tell me how well I did, basically. It's going to tell me the error. Okay, and we go look at this. And we see a telltale graph, which you are going to see again and again and again whenever you do machine learning. The telltale graph is this. Let's look at the blue stuff first. The blue stuff is the in-sample stuff. So what did I do to get this blue stuff? I basically took my training set. I fit the model on the training set. And then I asked the question that on the training set itself, what does my prediction look like as corresponding to the actual value? And not surprisingly, you find that there's some error to maybe start off with, but the error keeps going down and down and down and down and down and down and down. Remember, we said that we could perfectly interpolate 30 points of the 30th order polynomial. By the time we get to 30th order polynomials over here, and I'm interpolating, I'm going to go down to 0 error. Because I can do that, right? I can interpolate 30 points with the 30th order polynomial. So it's not surprising that on your training set, the error keeps going down and down and down and down and down, basically. The more complicated you make the training set, the more you're likely to capture all your points. But remember, we saw that earlier, when we tried to do that with the 20th order polynomial with the noise, that led to a lot of wiggling. And because that led to a lot of wiggling, that led to a complete destruction of any predictive power. And you can see this on the training set, on the test set when you do this. So what is this? What are the green points here? So the green points are the output of doing the following. I've trained this linear regression model on the training set, right? That's the place where I did the fit of X train. You can see that again up here. I think it's important enough that I should go up to it. That's this part. You trained it there. Now, to get the green points, I'm taking the test prediction, which is a prediction on the test set, and actually looking at it compared to the actual values. So when I do that, you see what happens. At first, because the lines aren't actually that expressive, right? Remember, we said that the curve looks something like this, and the line is kind of straightish, and it's not really doing a good job. I have some error. But then as I come down, as I go further over here, then I'm going to go to a point where I minimize my error. But after a particular point, when I minimize my error is going to start going to go up again and again and again. Because now what I'm doing is I'm making my model more and more complicated. It's wiggling. It's wiggling more and more. But it's not wiggling at the places where the test set points are. It's wiggling at the place where the training set points are. And so the error keeps going up and up and up and up and up and up. And so there's going to be a minimum, which tells you how expressive you can get away with being on the test set without being too expressive and still getting a predictive power. Now, this diagram is a diagram that you are going to see in each and every model you ever do in machine learning. You've probably seen it in some books in some stylized fashion like this, where basically you have some parameter that you're going along, which corresponds to the complexity of the problem. In this case, d, the degree of the polynomial, corresponds to the complexity of the problem. And you have this test set error, which basically goes down until you come to a certain complexity, and then it keeps going up again. Before it, you're underfitting. You're in that bias regime that we talked about right at the beginning, where you're not expressive enough. That straight line wasn't expressive enough to get that curve. It wasn't curvy enough. But then in the other side, you're in the very, very curvy part, where you're too curvy, and you've lost all predictability. And then when you get to the minimum test set error, that's when you know that that's the model you want. And that's the game. All of machine learning is a sort of variation on playing this game, where you basically try and get this, you try and minimize this test set error. Now, it's slightly more complicated than that, and I'll tell you why. The problem is this, that if the Lord came to you in your sleep and told you what this complexity D was, you'd be done. Having one training set here and one test set out here would be enough. But if you think about it, what we're trying to do in this plot out here is we have a second minimization process, and that's this minimization process with respect to the complexity. We're trying to find this complexity D. This complexity is what in the parlance of machine learning is called a hyperparameter. It's basically a parameter of the problem, so to speak. So remember that to get any one of these points, right, to get any one of those points on that graph above, what you did essentially was a minimization process. You did that empirical risk minimization we talked about earlier, and you fit the parameters of the, in this case, the 10th order polynomial to do it. On the training set, you fit the 10th order polynomial, found this error on the training set, and found that error on the test set. But you fit an 11 parameter problem. And then you say, oh, you know, the actual answer is over here, because that's where the test set error, or over here, because that's where the test set error got minimized. You're actually doing one more fit. So herein lies the problem. You are going to be overfitting if you just have one training set and one test set, simply because you have one more additional fit that you have to do, and you're doing this additional fit right on the test set. So it's not enough just to have a test set. You have now contaminated your test set, in a sense, because you're doing a fit for D on this test set. Remember that when you're trying to find this complexity D, you're finding it by looking at the error on the test set. So the fit for that one additional parameter in this problem, the hyperparameter D, is done on your test set, which means that it's really not a fresh piece of data to check your answer on in the long run. So that's why what you need to actually do is to not split the data into just two sets, but you need to split it into three sets, and the third set is what's called a validation set. So the structure of the problem then becomes like this, basically. You're going to have a training set. Now, this is kind of bad, right? Because you're actually now reducing the amount of data you have to train. But you have to do this. Otherwise, your answers are going to be a little bit too optimistic. So you have a training set. In fact, you can think about this was your old training set that we used, and this was your old test set. You take your old training set, and you now subsplit it into your new training set, which is a bit smaller, and a validation set. And the validation set does exactly what we did. We just changed its name. We're not calling it a test set anymore. We're calling it a validation set. You're going to train the model on this. You're going to fit the model on this, and you're going to do that once for each D. And once you do that once for each D, then on the validation set, you're going to look at the error, and you'll get one of those curves like this, and you'll find which one minimizes the validation set error now. And once you do that, you can actually test it on your test set, and this is a completely fresh test set. So now whatever error measure you get on your test set is actually representative of the real error of your algorithm. The one you got on this is not representative of the real error of your algorithm because you used it to make a fit. You used it to choose D, and now you got now you got the answer from that. And so then you go on to the test set, and you can check your final error. Okay, so that's the game you play. Now, once you have done this, what you can do, once you have found the D, what people typically do is then they will actually say, okay, using this validation set, I found that D is equal to 3 is the answer to this. And what they will do is they'll take this entire data set, and they will retrain the algorithm with D is equal to 3 on this entire training set plus validation set, and then they will use it on the test set and to make future predictions. So this way you get the best of both worlds. You trained it only on the training set, you found the hyperparameter on the validation set, and then you retrain it on this entire set over here, basically. And then you can finally test it on the test set. So in this way you get the best of both worlds. Okay, so I do that here. So I'm going to do this again for these, this 20th order polynomial. And this is the answer I get when I do it. I'll let you look at this. It basically uses exactly the same structure. We do this linear regression, then we do the fit, and then we use it, and then we do the predict. Again, make your model, fit your model, predict your model. It's the same thing for every machine learning algorithm. And then we calculate the error using the mean squared error function, which is also provided in scikit-learn. Okay, so we do this here. And when we do this here, we get some point over here, and we can also calculate the test set error, which is given to us by this red dot. And we can see the training error goes down. The validation set error now, remember our language has changed, goes up like this, and we get the minimum somewhere around here. Then we take that particular D we got for the minimum, and we retrain the whole thing on the training plus validation. And after retraining it, we calculate the test set error, which is what you do there. Now, if you're perceptive, you've kind of realized that this might actually have a bad problem, especially with very small data, where it may be thrown off by the sample you took. So what we did is, remember, we split this whole thing into this training error, this validation error, and this the training set, the validation set, and the test set. If this is small, you might just get something happening because of the non-representativeness of that particular thing. So what you do to prevent against that, and in fact, actually, let me just show that to you. I'll do this whole fit again. And when I do this whole fit again, you see this red dot move. Because my test set was just slightly different, and therefore my training set was slightly different, and therefore my validation set was slightly different. You want this not to happen. Besides, the other thing you want to do is, you've got all these errors, but how good are these errors? What's the error on these errors, so to speak? What happened if I changed the data set? If you remember earlier, because when I had those 200 points, and I knew those 200 points, and I created these different data sets of 30 points each, and I did those plots, I was able to show you all that hair. So I was able to show you how much error I had on the whole thing. So if I want to get a grip on how much error I have on this whole thing, I need to do something similar. But remember, I don't have the ability to choose 30 samples of 30 points from that entire 200-point sample. I just have those 30 points. But I can do something else now, right? Because I split this problem into this 24 and 6, 24 training set and 6 test set kind of things. And I split that 24 further into presumably, let's say, 18 training points and 6 validation points. I can mix up these 18 and 6. Right? So I can mix up these 18 and 6. This time it's this 18 and those 6. Next time it's going to be those 6 and those 18. Next time it's going to be those 6 and 9 here and 9 here. So I can mix up what I train on and what I validate on. And this process is what's called cross-validation, basically. And you can see it sort of like diagrammatically over here. What I do is I take this training set I had, this training area original training set I had, and this was the validation set. And I just do it in different ways. So here I made this particular part of it validation. Here I made this particular part of it validation. Here I made this particular part of it validation. So now if I do that, I can train on these 3, validate on that, train on those 3, validate on that, and I'm going to get 4 different answers. I'm going to get 4 different errors, and I'm going to get 4 different answers. And what I'm going to do is basically I will take the risk I get, or the error I get, on each one of these. I will add these together, and therefore giving me an average error. And I will do this for each D. So I'll calculate an average error for each D. And then I'll pick the one with the lowest average error for each D. But not only did it give me an average error for each D, it also gave me a kind of spread, because there are going to be 4 different errors I have the average, and I have the spread around it. So I can have an idea of how good, basically, my estimation of the error was and how good my picking out the smallest t was. So we can look at this. And this is kind of the entire process. We're doing that for thing. This is for straight lines. This is for flat lines, straight lines, quadratics, cubics, bloom, all the way up to 20th order. I do that for each one of these. In each one of these, I'm going to find the lowest what's called the cross-validation error now, which is the average error. And I'll find these averages, and I'll find the minimum of the whole thing. And we can go ahead and we can do this. And there are multiple ways to do this, but one way to do it is to use the scikit-learn function k-fold. This is basically saying it's a 24-point data set, and I want to split it up into 4 folds. So it splits this up, does a linear regression in each one, fits it, and it appends to this basically the results of the errors over here. I'll let you work out that code yourself, but you can see the answer of the whole thing over here. And I don't know if it's incredibly clear on this. Maybe I should reduce the brightness, I suppose. Wait, it's the other way around. It doesn't really do a very good job. But I don't know if you can see this particularly clearly, but that is a big band around this, which is basically telling you the entire spread of the errors you got from that particular cross-validation fold. And as you see, as you get to the higher sets, these are kind of quite spread out, the errors you get, basically. And remember, this is one of the worst problems you can get because it's only 24 points that you're training on. So I chose to take up a particularly hard problem to show you out here because of that specific reason. And you can see now that what it tells you, of course, is that the minimum is over here. And this is the test set error, and that's the error on the full sample over there. OK. How much time do I have?
8 minutes over.
Oh, OK. So I think I should stop here then. All right. So I'll stop out here, and then next time I'll go into regularization.